Good afternoon, everybody. This is the cranes presentation, and you will notice that this presentation is on YouTube because I tried to use Panopto. However, I'm suffering from technical difficulties and I'm forced to use this way, and I'm forced to have a very short presentation in terms of timing in order to reduce the recording time and to be able to upload it on YouTube. So, to make a long story short, cranes are either classified into either mobile cranes or tower cranes. Mobile cranes are either track mounted, truck mounted, or wheel mounted. The track mounted type is the one you could see up. The truck mounted is the one in the middle. The wheel mounted is the one at the bottom. Tower cranes are fixed or they are supported on rails with base ballasts to prevent them from overturning. And we will discuss the issue of the overturning moment. However, the major difference is that between them and the mobile cranes is that tower cranes could not carry a load and move with it. However, mobile cranes can do that. Mobile cranes could have different configurations. They could be crawler, they could be telescopic boom truck mounted, they could be lattice boom truck mounted, they could work on rough terrains, they could work on all terrains, or they could be modified cranes for heavy lifting. And as you could see, these are different sizes with different capacities with different technologies to tailor different needs. Mobile cranes, the selection of mobile cranes is a very simple process. However, it's based on two things. First, the capacity of the tower crane. Second is the dimensions of the tower crane. Sorry, the mobile crane. So the capacity of the mobile crane, as you could see, when the horizontal distance between the load and the center of the crane, which is we call the radius, when it increases, this capacity of the crane will decrease, as shown in this chart. On the other hand, the dimensionality of the thing is very important in terms of the boom length. The length of the boom is determined mainly by the dimension of the job that will be done. So, for example, if you have 100 feet horizontal distance at which the load is located, and it will move up to maybe a height of 90 feet. So that will mean that you will need maybe 110 feet boom. It will be just barely enough in order to, sorry, 120, that's 120. 120 feet boom will be barely enough in order to carry this load. On the other hand, the graph that was shown in the previous slide could be represented by tables, such as this table or that table. The difference between these two tables is that the first table is specific for a certain tonnage and a certain dimension of the boom. However, the second table gives you different boom dimensions that could work on the same truck mounted equipment. And if you could see the upper, there is a difference here differentiated by a line between an upper set of values and a lower set of values. The lower set of values are for large radii. So here you could understand that the mode of failure of such a case is actually due to overturning moment. However, the smaller numbers, their mode of failure is mainly due to structural failure within the cables themselves. So if I have a problem like that in which I'm having a load that's located at a position of 34 feet high, and it should move up to a position that's 114 feet higher. However, we have some attachments like the hook and the sling and the hoist of the crane itself. They have a dimension of 26 feet in height. So in such a case, we should add up all these numbers in order to understand that this is the size of this is the total height of the object of the boom that we should pick. And using also the horizontal distance, the radius of 70 feet, we will understand that the height of the boom together with this horizontal distance will give us 180 feet long boom based on the figure 17.12. If the hook, block, and sling weigh 5,000 pounds, in such a case, we need to deduct this number from whatever number that we'll be getting from the previously mentioned table. So the previously mentioned table will get us a 47,600 pounds based on the radius of 70 feet. So that means that actually the load that it could actually carry is this 47,600 minus 5,000, which is 42,600. Taking the picture to tower cranes, as mentioned before, they could be either mounted on rails or fixed in the ground. They could be attached to a structure as shown or freestanding. But of course, if you are attaching them to the structure, you could increase their height. However, the structure needs to be designed for that. The motion of the tower crane is actually three-dimensional. It could hoist objects up and down. It could, using with an aid of a trolley that has a motor in it, it could have a trolleying motion along its radius, along its saddle jib. It could rotate for 360 degrees around its oar axis. So it could move objects three-dimensionally this way. However, in order to understand mainly this tower crane, it will have one of two options. Either have one pair of cables, which is what we call the two-part line, or two pairs of cables, which is what we call the four-part line. And as you could see here, at lower radii, the capacity has been doubled when we are comparing the four-part and the two-part line, because the cross-sectional area of the cables have been doubled. And because these low radii, they represent the case at which a failure will happen due to structural failure, not due to overturning moment. So this is why for large radii, maybe 210 or whatever, the differences between these range of numbers are very trivial between the four-part and two-part hoist line cranes. Of course, having different jib dimensions will need different weights for counter weights. So the larger is the jib dimension, the larger is the counter weights we need. Also, because we know that we need a motor to do the hoisting and to do the trolleying motion. So in such a case, once you could simply understand that having a motor with a higher horsepower will simply give you the privilege of higher speed and higher capacity in terms of load. However, within the same motor, if you increase the gear, you will for sure have higher speed. However, you will have less capability to carry a load. So you will be less capable to carry heavy loads. So it's the same trade-off that we have discussed before with most of our equipments. So here we have a nice example. Can a tower crane whose load chart is shown as table 17.3 lift a 15,000 pound load at a radius of 142 feet. The crane has an L7 jib and a two-part hoist line. The slings that will be used for the pick weigh 400 pounds. So first thing is that we should add the 400 pounds to the 15,000. Then factor this up by a working margin of 5%. So now we'll have 16,170 pounds. and compares it to the number that we'll get from the table, which is 16,400 pounds. So now we found that this job could be safely done. I wish I was, I know I was brief in my presentation. However, I wish I was to the point and it was self explanatory. Thank you, and see you next week, inshallah.